Okay, good morning. Welcome to Collaborative Statistics, Chapter 12, Linear Regression and Correlation. So what is linear regression and correlation? Linear regression is a way to put a line, and notice here's to bivariate data. That just means XY data. So we have an X point and a Y, X value, an X value and a Y value. So to data where we have one variable dependent on another. So we have a whole bunch of points and we want to be able to stick a line through it. That way we can use it for prediction and basically see, does something happen to it. And correlation is the measure of the strength of that line. So that's what these two things mean, and we're going to talk about them a little bit. So we're not going to be using y equals mx plus b. From algebra, remember we had m was slope and b was the y-intercept. It's kind of like that, but we're not going to be, it's the similar formula, but we're no longer using m, we're using a, and b. Okay, so it's y equals a plus bx. A is still now the y-intercept, and b is now the slope. So we just kind of have to get that out of our heads of the old formula, and we have a new formula now that we're going to look at. Let me go back. So notice here, if we have a b bigger than 0, we have a positive slope. It's going up from the left to right. If it's 0, it's a flat line. And if it's less than 0, it's negative. It's going down from left to right. So those are the three things we get to look at for slope. We want to make sure, we want to see what happens with b here. Is this positive or negative? And when we look at scatter plots, this is the most common way to display them, is to just put some points in and show our graphs. Usually we'll have numbers eventually, but these are just standard ones. So we can see this has a very strong positive correlation. Okay, it's a strong positive line. This is a weaker one. I mean, they're still going up, but there's some points that are floating around the middle. And this has almost no correlation whatsoever. We could draw a line in any direction and not have anything. Where these two are now negative, we can see that they're going down as we go from left to right. This is stronger than this one is, because this one has points jutting out a little bit. And this here, we actually have a curve. So we have a linear relationship there and a linear relationship there, but in the middle it changes direction. So we don't actually have, we can't actually do regular regression, linear regression. We can do other regressions on this, but not linear. So these are the kinds of plots we're going to see. So to make them, all right, we go put our data into statistics, into our stat edit. All right, we enter our x data and our y data, and then we go to STATPLOT. All right, which is over here, second plot, a second y equals. I'll give a STATPLOT. We activate the plot. We want to make sure we have this one here. This is our scatter plot, and we can have different types of points if we have different a couple of graphs going on. And then we hit graph. We may have to do zoom stat to show it, but that's how we will see our scatter plot. From there, we want to be able to fit a line. So that's what the regression is. We're trying to fit a line. So we can draw a line through there, and we want to draw a line through the middle of the data so that we have points on either side. Okay, and there's a mathematical version of this, because we could draw that forever and we would not necessarily get the right one, which is called the least squares regression. And what this does is it finds the best fit, because it makes the residual errors, okay, which are the differences between the estimated point and the actual point, which are the residuals. When we square those, we have the smallest value. So that's why it's called the least squares regression, is because we square the residuals and we're trying to get the smallest value. So that's where these two things come in, and they're trying to fit the data. When we're done, we'll have an equation that looks like this. Where y hat, this is y hat, is equal to a plus bx. Oops. And to calculate b, we take the sums of our x's minus our means of x times our y's minus our means of y's, and divide that by x minus the mean of x squared. So we sum those things up and we divide. We will get our b. Our A, we find, just like in algebra, we take the mean value because this value will be on the point, on the line, and we multiply. So y bar, those are the mean of y, minus our slope times the mean of x will give us our A value. Okay, that will give us our y-intercept. Okay, so to do the regression in your calculator, you're going to, again, put your x and y data in to L1 and L2, which you've probably already done because you did a stat plot. Then you're going to go over to stat and calc, all right, and down all the way down to number 8. And notice here we have linear regression a plus bx. Yes, number 5 also has linear regression ax plus b, but since your book uses this format, I would suggest using number 9 here. This is wrong. Number 9, linear regression a plus bx, because that's the format your book uses, and otherwise you'll get confused if you look at the answers. And it's just helpful because it's going to ask you what was A and what was B, and you're going to, if you don't remember which one was supposed to be, you'll get them wrong. But you hit enter, and then it comes up with your equation here. So notice this is y equals ax plus b. Your A is this, your B is this, your R is this. Okay, and R is your correlation we'll get to in a minute. You can also do other things like telling it to put it into y1, so that way you can actually graph the equation. You can have it do it automatically at that point. You can have it do other things. There's some more things. You can have it come up with r squared as well down here, but I mean you can just square that and you get your r squared. So what this tells us is that, notice this is positive. Okay, B is positive here, so we have a positive slope. It's not a very steep slope, but it's a positive slope. This 0.91 tells us we have a very high correlation. You know, is it high enough to be useful? We can do some work and find that out. But at least we have some stuff to work with. So our residuals, all right, are just the error. Okay, we have E here, epsilon. Error is equal to the actual value minus our predicted value minus our y hat. So we can calculate our residuals in L3 and say, tell it, subtract the y values from the predicted values. So we can have it figure out our predicted values. Or actually, I think there's a resids formula. You can type it in there and it will actually bring up that value there for you in the calculator. So, but those things tell us, where we made our errors. Okay. That's all residual is just error from the actual. It's not that the problem's wrong, it's just that it's different from the actual information. Sorry, hit the wrong button. All right, so correlation. The correlation coefficient is R. All right, and all that is just a number. I don't know why they picked R. C would have made sense because correlation, but they picked R, and so it tells us how strong, big words here, the strength of the association between the independent variable and the dependent variable. So basically, is this regression line good? Is the fit decent? Is it a high enough number so that we actually know that they're telling us something? Okay, so the further it is from 0, the better. And it's going to be between -1 and 1. So the closer it is to -1 or the closer it is to +1, the stronger it is. Now remember, correlation does not mean we have causation. Okay. So here, every person who learned math in the 17th century is dead. However, learning math does not necessarily cause death. We only wish it did. Some of us. But so we don't have, just because correlation is high doesn't mean one causes the other. All right, and those are the things we have to remember. And here's this big, ugly formula about how to calculate R. And you're never going to do it by hand, so don't worry about writing this down and going, okay, I need to remember all this. But we have n, so the number of things, times the sum of our xy's, minus the sum of x's times the sum of y's, all over the square root of n times the sum of x squared minus the sum of x's squared times n times the sum of the y squared minus the sum of y's squared. So there's a lot going on there. Don't worry about it. You're not going to calculate it by hand. And again, going back to the scatter plots, notice they all talk about correlation. Positive correlation, negative correlation, no correlation. So these numbers here are going to be closer to 1 than this number. Okay. It's good. The number is always between -1 and +1, right? And it's the correlation R. The stronger, the higher the R is, the closer it is to 1 or -1, the closer the points are to the straight line. Okay, the line of best fit that we have. The smaller our residuals are. If R is 0, there's no relationship. If R is +1 or -1, all the points actually line up and make a straight line. So again, those things very seldom happen. You know, we very seldom get an R of 0, and we very seldom get an R of +1 or -1, unless we cheated. So don't worry about. You probably won't ever see those, but it gives you an idea of, well, what's happening. You know, where should the values be? And outliers can affect both of these things. I can have outliers, you know, that bring a line to be. So I can have a whole bunch of circle here and a line up here, and because there's that one point, it brings them all up, and it gives me a high positive correlation. And the same thing can happen. I can have a fairly straight line and then a number that just drops way out of space that makes no sense, and so now I have a negative, or I have a zero correlation or low correlation because of this one point that affected it. Okay, it may be real, so you can't just take the value out. We have to look at the data and see, well, does this make sense? What happened? Was there a typo somewhere? And that could occur, but we want to make sure we can't just remove the data and go, oh, well, we have a much better correlation now because of that. So those are things to look at. The sign of R tells us if we have positive or negative. So just like the sign of the slope. So that when we look here, the sign of our slope is B, will also be the sign of our R. They will agree. Okay. If R is positive, the values when X decreases, Y decreases, or when X increases, Y increases, we have positive. And here negative says when X increases, Y decreases, or if X decreases, Y increases, we have negative correlation. The correlation of determination is just R squared, so we just take the square R and we square it. It's always going to be positive, and it's a percent. And what it does is it tells us how much of Y, the variation in Y, is explained by the X values and the regression line. Okay, so it gives us so it's always a kind of a percent, and we'll tell it. It just gives us a value. Again, it says, oh, well, this much of it, because there's some things that will be explained by X and some things that won't, and so therefore we have to have that, and that's what R squared tells us. So, is it significant? Is it useful? All right. Well, we have a list. All right. We're going to take our n's. Right, in our book, we have a critical value table, and it tells us how many things are. We take how many n's we have and subtract 2. All right, so that's going to give us this thing called the degrees of freedom. We'll get into degrees of freedom in like chapter 8, so you don't have to really worry about what it means at the moment. But right now, you just know we have degrees of freedom, and we're going to take how many n's we have, subtract off 2, and we're going to compare our R to this critical value. If our R is higher than this, it's significant. If it's not higher, then it's not strong enough to make a prediction. Okay, and so that's what this means. So if I have 6 data points, I would look here and go, if my R is bigger than 0.811, positive or negative. So if it's negative point negative 0.845, it works. Okay, is the absolute value bigger than this of the R bigger than this? So if that's true, it's significant. I can use it to predict. If it's not, I shouldn't. And that's how we deal with that. Assumptions we should make that there is a linear relationship. Makes sense because we're testing a linear relationship. We're doing linear regression. We have to assume that there's a linear relationship. That the values of X and Y are normally distributed about the line, so that they can be anywhere. uh, it's all kinds of weird things. That the normal distribution is centered on the line. Again, you don't know what normal distribution is because we haven't gotten to it in chapter. That's in chapter 6 and 7. But basically, it's a bell curve, and that the means of those things lie on the best fit line. The standard deviations are equal, so we don't have vast, big spreads going along. And the residuals, there's no pattern. This is the most important one. Okay, that we have no pattern to our errors, because that if we have patterns, that means they all the errors tended to be at the end. So the end group really is where we would have to limit our best fit, because that doesn't make sense. Or if they're at the beginning, or if they start to make a sine wave or something, then we know we've made an error along the way. We want to have them random, is the big thing. So predictions, outliers. So predictions, we don't want to have things outside of our x's. So that's what this means by the domain here. The regression equation is significant. It can be used to predict within the domain, so within our range of x's. All right. If my numbers are between 1,000 and 2,000, I can't use my prediction line to guess something on that's 3,000. So it has to be within the space that I'm looking at. Anything that's 2 standard deviations above or below the mean, best fit, is an outlier. Okay, but we re-examine the data and we don't just remove it. Okay, if there's an error, we try to fix it or delete it. If the data is correct, you have to leave it in the data set. So outliers can happen. Bill Gates is an outlier when it comes to income. Sports figure, my favorite story is how North Carolina State the geology department used to report the mean mean starting salary of geologists, because one of their geologist majors was Michael Jordan, and so he brought the mean way up. He's an outlier, but he's a real data point, and we have to leave him in the set. Okay, we can't just remove it just because it doesn't make things pretty. So to calculate where the outliers would occur, if we look at page 534, example 12.2, we can, I put all the data into the calculator, and we run a linear regression t-test. Okay, and that gives us this value here, this S of 16.4. And if you look, you'll notice that when they've done the work, they found, oh, here it is. Is their S value. So we plug this into our equation, with our A and our B, and we can, within 2, because an outlier, remember, is within 2 standard deviations. So we multiply this value by 2, and then we add it and subtract it to our x values, our mean values, and we can actually find a graph. We can make a graph with that value, and anything that lies outside of that point would be considered a possible outlier. We could do, so if you're graphing it, and when you look at page 535, you'll see the graph, and you'll notice that there's a point that's above the line. We could do that on each individual value and say, okay, well, here's the values, this is what they're expected to be. Is there anything above this point? Is there anything below that? Does anything fall above or below? And we could check every one of those points out by hand if we had to. We wouldn't want to, but we could. And we could also take our error. Okay, we could find our residuals. And if you look on page 536, we have a table with all the residuals. And notice we could then say, okay, well, 2 times this value. So 2 times 16.4 is about 33. So anything bigger than 33, and we notice that the only value that comes to that is 65,175. There's an error of residual value of 35. So that's a potential outlier, and we would look to see, should it come out or should it stay in? And if we found that we made a mistake, that the number should have been 135, then we would fix it. If we realize, oh, this is if we can't find that if we find that it's a mistake and we can't find the original the correct data, we would remove it. If we find the right numbers, we have to leave it in. So this is what helps us with our determining if we have outliers on our regression from our scatter plots. So I hope that was helpful. I will see you in class.